Hello again, everybody. I would say good morning, but the videos, as you guys have probably been experiencing, take a while to upload, so good whatever time of day it is. Here's the do now, pause it, do it, all that good stuff. So picking up, here's the answers. Find velocity and acceleration of particle, blah, blah, blah. If you are given the position here, to find velocity, you take the derivative. Obviously, you have to use the product rule here. To find your acceleration, you would have to use the product rule in this part, and then just find the derivative of cosine of t for the second part there. Particle moves along the x-axis at a velocity if its position x is equal to 10, where's the particle when t equals 6. That is going to be an integration problem. You'd have to do 10 plus the integral from 0 to 6 of v of t dt. You get 82 off of that one. Find the length of the curve defined parametrically. Well, that's just that formula that we went over 2 lessons ago, where the length is equal to the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. Yeah. And then just plug it into your calculator to get that. Assignment, it's on my website, PDF, you can get it right here. Last class, we talked about very elementary vectors. Now, we will look at what can happen when we have variable vectors, meaning the size of the vector changes depending on another quantity, most likely time. So basically, we can have the components of a vector can be functions of the same independent variable. xy equals x of t, y of t. Basically, we have 2 separate functions for the horizontal and vertical components. If only we had a way to describe this like some sort of, like when we have a pair of functions. What I'm trying to get here is vector valued functions, which is what we're doing today, is really the parametric functions that we went over 2 classes ago. So just as a heads up, AP test, I know I've announced this in a couple of classes, but as far as the AP test is concerned, on the free response, you have number 2 comes from this chapter. So you have like a 50-50 shot of whether it's going to be a vector problem or it's going to be a parametric problem. So yeah, if you're taking the AP test, really you want to pay attention in this chapter. So look in here, we've got a particle moves in the plane, so its position at any time t greater than or equal to 0 is given by cosine of t, e to the 2t. Cool. Find the position vector of the particle at any time t. Well, the position is just a vector. It's those functions is what I'm trying to say here. Let's just make up a notation for it. Let's call it r. That's what our book calls it, just so you guys are clear. R of t is going to be equal to the vector cosine of t, comma, e to the 2t. So you can see all I did there was I took the parenthesis notation and changed it to the angular bracket notation that you see there. Can you guys tell when my desk, I'm kicking it or anything? Alright, so find the velocity vector of the particle at time t. Well, velocity, this was on the do now, velocity is just the derivative of position. So for b, let's just call it v of t. To find v of t, we are going to take the derivative of cosine, which, last time I checked, negative sine of t. Take the derivative of e to the 2t. Well, I've got e to the 2t times my chain of 2. Boom. Done with part B. Part C, find the acceleration vector of the particle at time t. Oh, well, g. To find acceleration, again, something that was on the do now, a of t is just going to be the derivative of v of t. So looking at that, derivative of negative sine of t, negative cosine of t, derivative of 2e to the 2t, it's now going to be with our chain 4e to the 2t. There we go, acceleration. Describe the position and motion of the particle at time t equals 2. So to describe the position and motion of the particle at time t equals 2, what we have to do is we have to find r of 2, which is going to be equal to cosine of 2, comma, e to the 2 times 2. Yeah. Handy dandy calculator. heads up, if we've done what we were doing last class recently in our calculator, we're probably in degree mode, so switch that bad boy back over into radian mode, and now we got cosine of 2, so approximately negative 0.416, comma, e to the 4, 54.598, holy dookie pants, that is large. Let's make sure my handwriting is easily legible so that when I come back and try to interpret, I can see it. V of 2 is going to be equal to negative sine of 2, comma, 2e to the 2 times 2. I wish I could just write that as 4. So, negative sine of 2, okay, negative 0.909, comma, it's just going to be this times 2. I really don't feel like doing that. 2e to the 4. Let's multiply that by 2 for the acceleration as well. 109.196. All right, cool. And last but certainly not least, a of 2 is equal to, let me see if I can do this, negative cosine of 2, comma, 4e to the 2 times 2. Well, I already got that part. It's 109.196. Oh, and actually I have cosine of 2. So, negative cosine of 2 is just going to be 0.416. Again, I'm just cheating. Cosine of 2 is up here. This is negative cosine of 2. It's just the opposite. And again, I've already typed this into my calculator, so 218.393. All right, cool. So what we can see here is the position of the particle. It is in let's see, negative, positive. So particle, let's try to speak good here. The particle is in quadrant, not quadrant 5, that's not a thing, quadrant 4, right? Down and right, yeah, that puts it in quadrant 4. It is moving, so what we can see here, the movement is described using the velocity. Velocity is going down and, wait, oh crap, no, left and up. Particle is not in quadrant 4. Just to be clear, negative, positive. It's very slightly in quadrant 2, but somebody would have called me on that if we were in class. It is moving left and up. And that, I'm just looking at the velocity vector, so the velocity vector will be left and up, so it's moving up in this direction, and actually it's moving at a really good clip there. It is actually turning to the right here. You can actually see, because the acceleration is an opposite sign from the velocity, it's actually turning around, so it's turning to the right and going up faster and faster and faster. Yeah, all that stuff, all work. Alright, here you go. Some stuff that you can copy down. It's straight out of the book. So yeah. Here you can actually see supposed particle moves along a smooth curve in the plane so that its position at any time. T is x of t, y of t, where x and y are differentiable functions of t. Particle's position, r of t. Now one thing to note, that is bolded, so it is a vector. Put the vector symbol above it. R of t is equal to the vector, x of t, y of t. Particle's velocity vector, v of t, derivative of x, derivative of y. Particle speed is the magnitude of v, denoted as magnitude of v. Speed is a scalar because we take away the direction from it. Particle's acceleration is a of t. Note that is a vector, so you put the vector symbol over it. Is the second derivative of x, comma, second derivative of y. Standard stuff. Particle's direction of motion is the direction vector v divided by magnitude of v. I've never seen this on an AP test. This stuff, yes. I mean this, number 5. I've never seen number 5 on an AP test. Didn't want to give you bad advice there. Alright, particle moves in the plane with the position vector below. Find the speed of the particle at t equals 2 and the acceleration vector at t equals 2. Find the slope of the line tangent to the path of the particle at time t equals 2 and find the position of the particle at time t equals 2. Good, good, good. Yeah? Okay, cool. So A, to find the speed, I know speed is equal to the magnitude of velocity. So speed equals magnitude of velocity, which is going to be equal to the magnitude of the vector, let's see, derivative of sine of 5t, well I know it's going to have a chain of 5 cosine of 5t, comma, chain of 3, so negative 3 sine of 3t. So the speed at t equals 2 is going to be the magnitude of the velocity vector at 2, which approximately is going to be the magnitude of, I think you guys can trust me that I am just plugging this in correctly, not plugging it in correctly, plug it in correctly. 5 cosine of 10, negative 3 sine of 6. Alright, so we have the magnitude of negative 4.195, comma, 0.838. That used to be the beginning part of my phone number. So here we've done magnitude of vectors. That was last class. So the square root of negative 4.195 squared plus 0.838 squared, which is approximately square root of squared plus squared 4.278. Speed of the particle at t equals 2 is approximately 4.278. Did we answer the question? No. We haven't found the acceleration vector yet. So a of t is going to be equal to the second derivative of position. Hey, I've got the first derivative of position right here. So a of t is going to be equal to chain of 5, so 25 cosine of 5t, comma, chain of 3, negative 9 cosine of 3t. Oh, I forgot it. Oh, jeez, oh, man. I'm really sorry about that. Forgot to take the derivative of cosine. Sine. Negative sine. And then we evaluate at t equals 2. The acceleration at t equals 2 is going to be approximately, let's see, negative 25 sine of 5t at t equals 2, so sine of 10, negative 9 cosine of 2 times 3, 6, oops, don't hit the plus. Alright, so the acceleration vector is approximately 13.601, comma, negative 8.642. Yeah. Alright, now we've answered that. Now to find the slope of the line tangent to the path of the particle, I have seen this in AP questions before. I mean, definitely I've seen speed. You will have to know how to find speed. Definitely I've seen acceleration. You will have to be able to find acceleration. And now to find dy dx, well, I think we did this the other day. To find the slope of the line tangent to the path, dy dx is equal to dy dt over dx dt. And if you don't remember that, that's from the parametric functions, section 10.1. It was 2 lessons ago. So look in here, I know that I'm doing this at t equals 2. So at t equals 2. Looking here, if only I knew what dy dt, oh, hey, look at that, I have that. Negative 3 sine of 6 over dx dt. Oh, hey, it's right here. 5 cosine of 10. And just so you know, it's okay to leave it like this. You don't actually have to plug this into your calculator. That is a perfectly fine answer, but just because I know some of you have itchy calculator fingers, negative 3 sine of 6 divided by 5 cosine of 10 gives me, no, that's not it. I did one of those mistakes that you kids do all the time. I didn't put the denominator in parentheses. It should be negative 0.1, negative 0.200. That 8 rounded up. Alright, cool. There's the slope. And it looks like because we have negative 0.200, the tangent line is going to be, slightly down. Gives us a nice feel for the direction of motion there. Look in here, part C. Find the position of the particle. Oh man, it couldn't be that easy. R of 2 is just going to be equal to 5 sine. I'm just going back up to the position vector right here. No. I'm supposed to be, but I wasn't. Alright, so just sine of 5 times 2, sine of 10, comma, cosine of 3 times 2, so cosine of 6. Which, again, okay to leave it like this, but just because you people and your calculators are out there, sine of 10, cosine of 6, we have negative 0.544, comma, 0.960. Oh, yeah. There we go. There you are. It's all worked out right there. Yeah, look cool, huh? Alright, whatever. Displacement and distance traveled. This is actually like the last thing that we have here. You can see, suppose a particle moves along a path in the plane so that its velocity at any time t is v of t equals v1 of t, v2 of t, where, this is a vector, so I'm just going to change that. That should be angular bracket thingies right there. Where v1 and v2 are integrable functions of t. The displacement from t equals a to t equals b is given by the vector integral from a to b of v1 dt, v1 of t dt, comma, integral from a to b of v2 of t dt. My reading skills are not up to snuff right now. The preceding vector is added to the position at t equals a to get the position at t equals b. The distance traveled from t equals a to t equals b is the integral from a to b of the magnitude of v of t dt. And magnitude was given last class. Really, this is stuff you've done before. Displacement is the integral of velocity. This was, 2 chapters ago on applications of integration. Distance traveled is the integral of speed right here. To find position, add your displacement to your initial position. Pause if you need to write this down. And I'm moving forward, always moving forward, never moving backward. Alright, velocity of particle moving in the plane is given below, along with the position of the particle at time t equals 3. Find the position of the particle at time t equals 3. Okay, position. Again, we just figured out position is take your displacement and add it to the initial condition here. So the position at time t equals 3, I'm just doing number 1 for you right now, is going to be equal to the initial condition, 7, 2, added with the integral from beginning of time to end of time, okay, this is a typo. This is a typo right here. If I give you the position of the particle at time t equals 3, well, the position at time t equals 3 is just 7, 2. This was supposed to say at time t equals 0. Oops, my bad. So now we can do 7 to 2 of the integral from 0 to 3 of 2 pi cosine of 4 pi t dt, comma, integral from 0 to 3 of 4 pi sine of 2 pi t dt. There's all the work. I know this is going to be difficult to do because we definitely want to do this by hand. Never want to plug it into a calculator. Ever. 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 That was sarcasm. I know you guys have been away from me for a week, so not really familiar with it. In case you can't see what I'm typing into my calculator, I think you can, but in case you can't, I'm just doing 7 plus integral from 0 to 3 of 2 pi cosine of 4 pi t. I guess technically I'm using x. This is 7. What? I guess it didn't move anywhere, right? Well, I guess we really do have to check the other one to see if it moved anywhere. 2 plus integral from 0 to 3 of 4 pi sine of 2 pi t dt. 2. Okay. It started at 7.2 and it ended at 7.2. That means it definitely didn't go anywhere, right? No. No, that's not what it means. That just means it ended where it started. In order to find out if it went anywhere, we have to do part B. Again, this was part A. Part B, we actually have to find the distance that we've traveled. So the distance is going to be the integral from 0 to 3 of the absolute value, the magnitude of v of t dt. Okay, this is going to be messy. Looking here, we can call this the integral from 0 to 3 of the square root, I hope I have enough room, of the x component, 2 pi cosine of 4 pi t squared, plus the y component squared, 4 pi sine of 2 pi t squared, and then a dt hanging out there. Okay, this is too much for me to plug into my calculator. So a nice little life hack that I can do. I'm going to change this into parametric mode. Go up here, type the x component, 2 pi cosine of 4 pi t, into the x1, 2 pi cosine of 4 pi t, type the y component into y1, 4 pi sine of 2 pi t. And now on my home screen, because I can use the vars menu, I can now do fn int from 0 to 3 of the square root of x1 squared plus y1 squared dt. Thinking. I was really thinking. Oh, there we go. It's nice and quick calculation. And there's the distance that's covered. So it actually went 28 and a half units, but ended up where it started off. It's just like when I wake up in the morning and go for my run. I hope my displacement at the end of my run is 0, or else, again, really awkward for wherever it just showed up. Oh, hey, wow, this is from 2011, AP question. Again, you guys know about AP Central. You can go to AP Central and find that. I'm just gonna, I guess I can run through this with you guys, right? You guys trust me to run through it with you? So the first thing that I like to do in these problems, I note that I've got dx dt and dy dt. That means, defined for me already, I have the velocity vector. What I like to do, just like I showed you guys in that last problem, I like to go in and plug in 4t plus 1 and sine of t squared. Just putting that into my calculator right there. Right? Am I good so far? Yeah, I'm good so far. Find the speed of the particle at time t equals 3 and the acceleration vector of the particle at time t equals 3. Okay, so both of them are at 3. All right, well, that's good. Next thing that I can see here is to find the speed of the particle at time t equals 3. So speed, part A, speed is going to be equal to the magnitude of velocity at t equals 3. So speed is equal to the magnitude of velocity. Okay, well, I already have the velocity right here. So this is going to be equal to the square root of dx dt evaluated at t equals, 3 squared plus dy dt evaluated at t equals 3 squared dt. Alright, cool. So, actually I'm cheating here and I'm looking at AP. They actually put it a little bit more succinctly. They called this x prime of 3 squared plus y prime of 3 squared. Oh wait, no dt. Ugh, I can't believe I did that. And then you just plug it into your calculator. Since I have those stored in as x1 and y1, what I can actually do is, on the home screen, square root of alpha x1 of 3 squared plus alpha y1 of 3 squared, and then I hit enter. We got 13.007. However, AP does accept 13.006. Truncation also works. Acceleration vector, A of 3, is just going to be equal to x double prime of 3, comma, y double prime of 3. And I know it's kind of scary. You have to take, well, the first one shouldn't be scary. The first component, let's put it approximately because I don't think it's going to be dead on. First component is just going to be 4. Derivative of 4t plus 1 is just 4. For the second one, all I do is go into n derive of y1 at t equals 3, and I get negative 5.467. Okay, we've finished part A. Before we finish up parts B, C, and D, somebody just came up here, and I think she wants to say hello. Do you want to say hello? Okay, my daughter is sitting up here, and she's just watching me do some calculus, so, you know, fun times. She's whispering to me because she doesn't want to talk to you. B. Find the slope of the line tangent to the path of the particle at time t equals 3. Okay, slope of the line tangent. Oh, we've done this already. dy dx is going to be equal to x prime of 3. Nope. Got that upside down. Y prime of 3 divided by x prime of 3. Which, again, I mean, I'm just going to plug this into my calculator because I have it available to me. Fraction, y1 of 3 divided by x1. I said divide by x1 of 3. Enter. Hey, cool. Approximately 0.032. cool. There we go. Find the position of the particle at time t equals 3. Well, position of the particle, I know that I have x of 0 is 0, y of 0 is negative 4. To find x of 3, all I have to do is take the x coordinate at t equals 0, add to it, integral from 0 to 3 of dx dt. Find y of 3. All I have to do is take the y component, so negative 4, plus integral from 0 to 3 of dy dt. And I just plug them into my calculator. FNN, oops. Forgot to do, I don't have to do 0 plus, do I? 0 to 3 of x1 dt. And, oh, cool. Integral 21. Negative 4 plus integral from 0 to 3 of y1 dt. That one's not exactly dead on. Negative 3.226. So at t equals 3, the position is 21, negative 3.226. There we go. And last but not least, D, find the total distance traveled by the particle over the time interval 0 to 3. Okay. Distance is just going to be the integral from 0 to 3 of the square root of the x component squared, x component of velocity rather, plus the y component of velocity squared. And now we just have to plug it into the calculator. Integral from 0, whoopsies, not 0, 3, 0 to 3 of the square root of x1 squared plus y1 squared dt, which is approximately 21.091 units, whatever the units are. Alright, cool. There's AP Test 2001. It's actually an anomaly that it was question 1. It's usually question 2. But whatevs. 1 is usually the rain and drain that I gave you guys from Applications of Integration. There's your assignment. Don't forget to smash that like button.